EDX Core Pure roots of equations, forming equations with related roots by a substitution method. In the last session we looked at the roots of the original equation, and the roots were alpha, beta, gamma. The new equation that we formed had roots 2 alpha, 2 beta and 2 gamma, and we noticed that there was a horizontal stretch by a factor of 2. So for example, where the old equation had a root at 2, our new equation had a root at 4. This effect can be achieved by halving x. In other words, if we substitute x over 2 instead of x, we can create that horizontal stretch along the x-axis. So this suggests another method for deriving a new equation. In 2x cubed minus 5x squared minus x plus 6 equals 0, we could let x be substituted by u over 2 to create that horizontal stretch by a factor of 2. So x is going to be substituted by u over 2 cubed minus 5, again the substitution u over 2 squared minus u over 2 plus 6 equals 0. Simplifying each term, we get u cubed over 4 minus 5u squared over 4 minus u over 2 plus 6 is 0, which is a valid answer, but it would make more sense to simplify these coefficients by multiplying through all the way through by 4. So we get u cubed minus 5u squared minus 2u plus 24 equals 0. And what we would normally do now is we've created an equation with the required roots by using the substitution. What we would normally do now is to replace the variable u with a new variable x. So instead of u, we'd call it x. 5u squared becomes 5x squared, minus 2u becomes minus 2x, plus 24 equals 0. So just to note, in that last line we haven't used the original substitution. All we've done there is change the variable. So we've gone from variable u to variable x, which is what we would often do at the end of a question. Okay, so that answer there is a perfectly valid answer. The variable is called u. You could change the variable to an x if preferred. So a slightly more intricate problem here. We've got a cubic with roots alpha, beta, gamma, and we're trying to find an equation with the roots 3 alpha plus 1, 3 beta plus 1 and 3 gamma plus 1. So we could do this problem using the previous method on the previous presentation by looking at the sum of the new roots, the sum of the pairs and the product. But we can also do it by a substitution method. Let's introduce a new variable u, which is 3 times the old variable x plus 1. In other words, x is the same as u minus 1 over 3. So if we now substitute for x in the original equation, we should be able to create a new equation with new roots called 3 alpha plus 1, 3 beta plus 1, 3 gamma plus 1. So I'm now going to substitute for x in the original equation. So that's u minus 1 over 3 cubed plus 4 u minus 1 over 3 squared minus 2 lots of u minus 1 over 3 minus 6 is 0. I'm going to multiply all the way through by 27 now, just to make the coefficients much neater. So that'll give me just 1 u minus 1 cubed, and after simplifying it'll be 12 u minus 1 squared minus 18 u u minus 1s minus 162 equals 0. So we need to expand all this to get our polynomial in u. So doing a little expansion of u minus 1 cubed with or without Pascal's triangle as preferred, I get u cubed minus 3u squared plus 3u minus 1. Then expanding 12 lots of u minus 1 squared gives me u squared minus 2u plus 1 minus 18u plus 18 minus 162 is 0. And now if we collect like terms together, there's 1 u cubed 9 u squared minus 39 u minus 133 equals 0. And just to clarify this final step, that is a perfectly satisfactory solution to the problem. That cubic equation in u would have roots 3 alpha plus 1, 3 beta plus 1, 3 gamma plus 1. But we often just replace the variable u at the end with the variable x. So it becomes the more familiar x cubed plus 9x squared minus 39x minus 133 equals 0. That's the more familiar solution. As we can see there. In the next session, we will be solving polynomials with complex roots.